All right. A little delayed with the intro talking about COVID. So did anyone come in? I'm sorry. Did you come in late? Did you have your? But I got everyone right. Anyways. The chemistry class should probably start by talking about what chemistry is. Chemistry is the study of matter and its changes. That's the definition of chemistry. Chemistry, there's kind of like science, but we also known as natural sciences. We have kind of three main branches. So chemistry, but I'm biased, I'll put it first. Physics is the study of the physical world. To me, physics is how long the vector is and where it points. So here's my center of mass. My weight is pointing down towards the center of the earth. I have the floor is pushing back with a normal force. So my weight and the normal force cancel each other out, and that's why I'm not falling. So that's, I know there's a lot more to physics, but that's physics in a very brief nutshell. Biology is a study of living things. And there's other types of sciences too, oceanography, geology, study of the earth is geology, oceanography, study of the ocean, but kind of, the big ones are chemistry, physics, and biology. In chemistry, you study matter. So we study matter. And before I get into there, has anyone heard of dihydrogen monoxide? So dihydrogen monoxide, it is a greenhouse gas, very powerful greenhouse gas. It's 80% stronger, or it's slotted to cause 80% of global warming. It is 500 times as powerful as CO2 when it comes to its greenhouse gas abilities. They use it in Fukushima. They find it in cancer cells. Animal research uses it. And there's a huge investment on its use in warfare that many people don't know. You breathe it, yes, it's true. Another little known fact. Yeah, well, and yes, you breathe it. It can, not only that, it can cause horrible burns. So it's a painful death. So this is, I'm kind of building up to a joke. Does anybody know what dihydrogen monoxide is? And my pen. This is like my worst day for technology.
Is it water?
Yeah. Dihydrogen, H2, monoxide O. Dihydrogen monoxide. Everything I've written here is true. Okay, good, we're working. Dihydrogen monoxide. So it is a greenhouse gas. And if you study climate change, the idea is climate forcing. So carbon dioxide is a pretty weak greenhouse gas, to be honest with you. It's and the idea though, carbon dioxide causes more water to evaporate in the oceans, and that's the idea behind climate forcing. It's actually the water vapor is what does the global warming. So Fukushima, it's a nuclear power plant. We use water to cool things in power plants. It's there. It's found in cancer cells. Yep, there's water in cells. You gotta give the bunny rabbits water in animal research. Huge investment in warfare. Anyone ever heard of the Navy? Mm-hmm. So it's everything here is true. And this is my attempted hook for you. So one of the things about studying natural science, like chemistry and other sciences, you can kind of start to see through some BS, right? And you can see there's a lot of BS out there. And I guess I'm being a bad speaker. I'm apologizing to you too much. I do take speech classes. Don't apologize to the audience. Here I am apologizing. We're going to change topics a lot, especially in the beginning. We'll get a little better as we go on, but one of the reasons why people hate this class so much, and I love chemistry, but I understand that I don't think anyone, there might be one or two that are here for personal interest, but most people are taking this class because it's a requirement. And people don't like this class because there are so many mental models. So you come to class, you're going to get a new mental model quite a bit. So yeah.
Where would you classify organic chemistry, biological?
It's usually considered synthetic. Yeah. So, and you sometimes say cooking is a science. sculpting is a science. What does it mean to call something a science? It means it's systematic. So a science defined is a systematic approach to solving problems. And this type of science we're talking about specifically is a natural science. So this is different than, say, a social science. So psychology, political science, and sociology are social sciences. They don't follow the same rules as natural science does. So specifically in the scientific method, their scientific method is different. So the scientific method for social science is this kind of collect data and generalize. And whereas a natural science, we are, at least nowadays, we are, when I say nowadays, we are into data-driven science. So where we have observations, so you start with observation, observations are data. So, and data can either be quantitative or qualitative. So quantitative means numbers. You have a number to something, it's a quantity, it's quantitative. So qualitative is an idea. So this is a relatively small classroom size. So that's a qualitative observation. So I could say this room is about, I don't know, 8 meters by 4 meters in length and width and a height of about 3 meters. That's a quantitative, because I have given numbers to it. I'm sorry, the other. Okay, and so then so we have observations, and you have observations that form a hypothesis. I've actually given you guys hypotheses as my answer when you guys are asking about COVID. I gave you hypotheses for some of the responses. And I also pre-noted it with, this is my opinion. So I kind of in scientific jargon, I'm like, I'm presenting you with a hypothesis. So like when you ask me, why is Moderna's worse? It's like, maybe it's a dosage. I would hypothesize that. And not only that, I propose an experiment, because when they have the 50 microgram booster shot, maybe it won't suck as much. So that's your experiment. So then that you would either confirm the hypothesis or you would reject the hypothesis. If you reject the hypothesis, something else. We need a new hypothesis. So, and then if enough hypotheses are confirmed, you can have a theory. A theory is a proven fact. And theories can and often are wrong. So a very powerful theory is the Greek theory that there are 4 elements: earth, wind, fire, water. That's a really powerful theory. I mean, it really changed the way we thought about things, and it can explain almost everything using that theory. Of course, it's wrong, right? I mean, so they thought air and fire were sort of anti-gravity, and water and earth were sort of gravity, and explain why. If I take a log and I burn the log, and all the fire is gone, it won't burn anymore. And you can feel the air coming from the fire. That's the air. You're left with ash. That's the earth. And I can gather there's some water here too. So I have all the elements right there. I mean, that explains why wood burns. And you can predict things also with that. So, and they can be right, but you can also be completely wrong. And and of course, contemporary atomic theory is much superior to the earth, wind, fire, water model, right? So, and some of the theories, if you look at them, it's kind of scary what we base our knowledge on, to be honest with you. Like the standard model of physics. I mean, it's almost like, well, we're doing the best we can. And you can refine the theory. So once you have a theory, it doesn't mean that it stops there. We keep on refining it. So, and some theories are very well formed. Some theories are not very well formed. And I mean, like, so astronomy, for instance, is full of some of these theories. I mean, like dark matter and dark energy. Like we understand gravitation, but we don't understand the orbit of the galaxy. And so it looks like there's matter there, but we can't find it, so we're going to call it dark matter. You know, and the universe is expanding. We don't know why it's expanding faster, accelerating. It's dark energy. You know, this is our way of saying we have no idea what's going on.
Watch Star Wars a little.
Oh yeah, dark. It's the Force. Yes. Okay. And I guess I should talk about chemistry. This is a chemistry class. Chemistry, we study matter, and the main types of chemistry. This is not necessarily in the book, but as a chemist, and but I know most of you aren't going to be chemists. But we tend to have we have 2, maybe 3 branches. So synthetic chemistry. This is your Walter White from Breaking Bad. This is the people that actually make things. Then you have a physical chemist. I don't know, maybe I'm starting to show my age. I know this is still cool. Did you guys watch The Big Bang Theory? Not really. You know, okay. No. Leonard, if you know Leonard, he had a table with a bunch of laser table. That's what I did in grad school. I'm a physical chemist. So that's the kind of chemist I am. And actually, most people that teach general chemistry are physical chemists. Another fun fact. So, and now we have more of an emerging field of biological chemistry, biochemistry. So we decided to give its own branch. It used to be synthetic, but it got to be too big. So to me, I mean, I tend to think of things really small, and biomolecules are just huge. So so much so that you kind of have to look at them in a different way. You can't look at them in terms of the individual forces they're going through. You have to kind of group them and their shape and how they interact. And that's like when I showed the spike of COVID in the first class. I guess I didn't explain that. Some of the things on that picture were an alpha helix and a beta sheet. It's just the protein structure. So when we do that, we're not going to do that in this class, but if you study biological sciences, they group things like that into kind of general shapes and categories. So a different way of thinking, we give it its own field. Oh, and I forgot to mention what a law is in the scientific method. So a law is a summary of observations. So when you hear a scientific law, it is a summary of observations. It can be math-based or it can be idea-based. So it can be quantitative and qualitative. Newton's second law. Force is mass times acceleration. Right? That is an equation that we use. And this is scientific law. The ideal gas law. We will study this in this class. Pressure times volume equals the number of moles, gas constant times the temperature. That is the ideal gas law. So there are other laws that are not quantitative. So law of gravity. What goes up must come down, kind of an idea. Right? Can you break the law of gravity? Yes. Rockets, right? Those go up, they're not coming back. Voyager probe's gone. You can break certain laws like entropy. Law of entropy, second law of thermodynamics. You can break that. It's very rare, but it's possible to. So, but laws are not, absolute. So they can be broken, and they can also be broken under certain circumstances. So, and I mentioned this as natural science. So if you want to know how social sciences work, and I do recommend you take social sciences, they're interesting. I'm not very good at them, so my understanding of them is kind of rudimentary. So take sociology, for instance. So sociology, they have theories. They they are theories. They're social science theories. So you take something like the purpose of a family. So we have a family and you have different theories in sociology. So you have, for instance, conflict theory. And the conflict then between the members of the family is what defines the role. So conflict theory is everything is about conflict. So the conflicts that people face define their roles, and whatever it is they're doing in a family, it defines the roles of family. Then you have functional theory. So where a family exists to serve a certain function. It could be for financial reasons. It could be for raising kids. So this is probably the best example for a nuclear family would be the nuclear family exists to have a function in society to help rear young. And then you have things like feminist theory that say the purpose of things are to set gender rules for women. So feminist theory would say that one of the reasons for family is to put women in a certain place. So, and then to further the oppression of women. And which one of these is correct? And the answer is they're all correct. So because social sciences is a generalized thing, where something like human behavior is just too complex to society. So, I mean, does that mean that, like, to me as a physical scientist, I have a hard time with this. If I have sodium and I throw it in water, it explodes. And if it doesn't explode, it means it's either not sodium, it's not water. There's never going to be an instance where I throw sodium in water and it's not going to explode. So, but with human interaction society, this is a different thing. I can run a red light one day, and the next day I run a red light, I get a ticket, right? I mean, that's simple, there's a comp there, but let's say, certain behaviors, like I get into a fight with my wife and I respond by giving her chocolate. And I get, then everything's fine. Is that going to work the next time? I mean, it's hard to say. But that's human interactions, and it's just much more complex than something like throwing sodium in water. So, and it's just a different way of thinking things. So, and whereas in social sciences, you can have many correct answers, and you have many different viewpoints. Science tends to be a little bit more yes or no. I mean, of course, many things are open to interpretation, like what's the best vaccine? I can tell you my opinion, but, does that mean that, like we already know, but I think Moderna, does that mean, is that the new fact? Is Moderna going to be the best vaccine forever? I mean, it depends on whom you ask. And I mean, with the vaccines, even so, like the Johnson & Johnson vaccine, like, Johnson, but it's great because it has a huge shelf life. So if you want to get the world from being naive, it's great to get the rural areas versus. So, I mean, does that mean it's a better vaccine? Like, well, depends on what you're arguing. So if you're doing effectiveness, it'll probably be Moderna. If it's availability to all the population of the earth, it's going to be Johnson & Johnson. So, okay. But we're in natural sciences, so we don't do the same type of thing as social. And I do recommend, of course, I'm an educator. Of course, I recommend you take more classes. So take your social sciences and enjoy them, please. So I'm not knocking on them. They're just different than natural science. And I mentioned this. Oh, and science is tentative. And this has been this way since about the 1850s. Like science used to be philosophy. So specifically, and very, very Platonic. So Plato. So Plato literally believed that there was a form in heaven, like if you had a chair, or he didn't have I don't know, I guess a chair. I know this is an Apple Pencil, but the most perfect chair is in heaven, and then you relate everything to that chair. So it's kind of like Platonic was kind of relating some idealized form, or his republic, for instance, it's the idealized sort of society. And we even say the word Platonic love, for instance, but it's not the same as in Greece. Platonic love was only between two men. So women were incapable of really experiencing love. So, I mean, although we say, we misuse the word Platonic quite a bit, at least in the Greek form. So, but like I said, science was a lot about philosophy. And then we had a switcheroo to experimental data, the age of reason, as we called it. And I mean, now natural science has just taken off. So that switch from philosophy-based to data-driven. And we still have this data-driven type of idea with natural science. So, and we even use the words like string theory, for instance. So string theory is not a valid theory in natural science. String theory is proven by mathematics. So, but as of yet, we do not have a case where string theory predicts pretty much the same thing as quantum mechanics. So the major theories holding up physics right now are quantum mechanics and general relativity. And string theory has predicted a few things that quantum mechanics doesn't predict. So we're looking to see, like right now, there's a lot of experimentation going on to see if we can find those things. So if that happens, quantum's out, string theory's in. So, but that's science today because it's experimentally based. So string theory, as I said, is not considered a valid, I mean, people study string theory, but it's not considered a valid scientific theory yet because it hasn't been experimentally proven. And another big thing, correlation does not mean causality. That's a big thing in science. So there's many times people have a common third factor. So this is one of the ways you can tell if someone is kind of giving you BS, is using the word correlation and causality. Social sciences do this quite a bit. And I'm saying that they're not natural science. So, I mean, you can have oftentimes a common third factor. So, I mean, something like, okay, so let's talk about another epidemic we had. We had polio, and people correlated ice cream sales to polio outbreaks. And so they said, you know what, when we see a large increase in ice cream sales, we are going to see more polio cases. And so people say, well, you know what, parents, if you love your kids, don't buy them ice cream. That's a take-home message. And that's not the reason why. It's because in the hotter months, people intermingle more. When it's hotter, people buy ice cream. So that's what I mean by correlation does not mean causality. I mean, we can correlate all sorts of random stuff. I could probably take a survey and I could ask you guys, how many peanut butter sandwiches have you eaten in the past month? How many flat tires have you had in the past year? Like, would I, is it feasible I could find a correlation between peanut butter and flat tires? And the answer is yes. Does that mean that one of them correlate, that cause one or the other? The answer is no. No. Also, science is powerful. It puts people in jail, right? I mean, and it's protecting, like for me, for many of the people with the therapeutics for COVID, I mean, and the vaccines, it's powerful. It's doing its work. But also bad science can severely injure people. So that's the token that science is very powerful, but bad science is also very powerful. So, and this is my opinion. This is not necessarily in the book, but I mean, this is not my opinion, but there's a science field called eugenics. So that was right after Charles Darwin came out, they came up with eugenics. And the idea is with eugenics that there's different races of humans and that there's a superior race and there's inferior races, and actually the inferior races should go extinct and the superior races should not go extinct. And if we need to make sure this happens, otherwise it'll cause the end of the world. And some people still believe this. So, and many people believe that. And for instance, it was very popular here in the United States. We sterilized about 300,000 women, specifically Puerto Ricans. So here in the United States, because of this inferior race. And we still use the word race. It's so stupid. So there's only one race, it's the human race. It's the Homo sapiens sapiens. Right? So if you study biology with a species, if two members of the same species mate and they produce a fertile offspring, then they're the same species. So that is the scientific definition. I mean, of course, there's a little bit of gray area with that because there's certain species that are close enough. I mean, so humans, for instance, have intermingled with Neanderthals. So we have Neanderthal DNA in us. So, I mean, but generally speaking, I mean, if you can generate a fertile offspring from another individual, and if you can do that, then you're the same species. And so that is the real definition of race.
I think Watson thought eugenics was really prominent.
Oh yeah.
Yeah.
Oh yeah. Yeah. Yes. And I mean, and many laws too, the miscongenation laws. So it wasn't until 1967 that, I mean, if this was before 1967, I would be in jail right now because my wife is Asian and I'm a white person. So, and prior to 1967, you could go to jail if you were considered Caucasian, what we consider Caucasian, and if you were to marry a non-Caucasian. So the idea was, because if we did that, then it would cause the end of the world. So, and I mean, of course, it's complete, utter non-science, right? That's bad science. So, and it's powerful. Bad science is also powerful. What do you know about bad science? It uses correlations, heavily relies on models, and models are fine, but they need to be experimentally verified. The experimentation of that is, and consensus. That's another thing. Consensus doesn't matter how many people think it happens. Einstein had one of his best, slams back. With the Nazis, Einstein was a Jew, and the Nazis, they had their own science, and what they considered science, but they didn't consider science. And Einstein was Jewish science, wasn't real science. So they thought, for instance, there was ether. The ether was around us, not this, general relativity. And so there was, I think, 10,000 scientists against Einstein, and his response was, if they were right, it'd only take one, or something along the line. So, that's doesn't matter how many people think, it's the proof. So, okay. Anybody have any questions about what's science and what's not, what is science, what's not science? Nope. Okay, so chemistry is the study of matter, and I know we're changing topics. So matter, what is matter? Matter is something that has mass and volume. So that's one of the definitions of matter. So I mean, I can go further. We can talk about so fermions and bionic matter, but we're not going to do. We'll stick simple. This textbook here is made of matter. It has mass. It's heavy. I can feel it, and it has volume. This has mass and volume. This is made of matter. Can anyone think of something that has volume but does not have any mass? What's that?
Gases not have mass.
Gas have mass. Anyone think of anything that has light? Yeah, light energy. Light and energy have volume but don't have mass. So there's nothing though that we know that has volume but does not have mass. So, but light energy, they're a little different. We can talk about it a little bit more when we get into further chapters. We're going to say something else, or you? No.
No.
Okay. And so solid. This is a solid. This has a set shape and a set volume. That's what solid means. Defined shape, defined volume. Liquids. I left my water bottle at home, but if I had my water bottle, I'd be like, what's the shape? What's the volume? Like, well, the volume is about 1/2 liter, and the shape is a cylinder. Now I'm gonna turn on its side, like, what's the shape? What's the volume? Well, now it's kind of like a cylinder, but cut this way, and it's still 1/2 liter. So liquids have set volumes, but they don't have set shapes. So, and then you have gases. So air is a gas. Gases have neither set shapes nor set volumes. So you bring a tire, like, what's the shape? What's the volume? Like, well, that's sort of I don't know, what's the blunt thing called? Anyways, it's the shape of the tire, volume of the tire. You slash a tire. What's the new? It's the shape of the room, volume of the room. So gases have neither set shape nor set volume. And also, solids and liquids are known as the condensed states of matters, a condensed state of matter, and gases are known as the vapor state of matter. So, and at least here on Earth, so this is mostly here on Earth, Solids and liquids have much more matter to them, generally speaking, than gases do. So, I mean, you can feel the air. You can rev your arm in the air. You can feel it. What happens if you do that underwater? It's, you got to push your arm out of the way because on average, there's about 1,000 times as much matter in water than there is in air. So that's why we call it condensed state. Also with solids, there's two types. There's crystalline and there's amorphous. So crystalline means regular pattern, amorphous means random pattern. So you can get metals. I worked with single crystal metals in graduate school, and metal, so I worked with iron, and it was a set crystal. Everything was it was really hard to make. You can get, everything was very, very organized. If you took a hunk of iron and then, it's going to be amorphous. So if you take a hunk of iron that you rip off of weight in the weight room, pumping iron, that iron is going to be amorphous, irregular. So another one, okay, sapphire. Sapphire is aluminum oxide. So that's what sapphire is. And if you take aluminum foil and you look closely at it, it's got white flakes on it. Those white flakes, that's sapphire. That's aluminum oxide. So you can get the gemstone crystals. That's a very set regular pattern, and you have amorphous sapphire on the top of your aluminum foil. So that's, that's probably a better example than what you're doing with iron. Okay, and here's some pictures here showing solids, liquids, and gases. I guess I described them. So we answer my questions? Nope. All right, and now we're gonna break everything down. So changing topics yet again. So do I want to start small or want to start big? I'll start big. What the heck? Most everything we find in nature is a mixture and it's heterogeneous. So hetero means different, homo means same. So heterogeneous mixtures, so I am a heterogeneous mixture. So, and okay, here's another one, wet sand. It's water and sand, two different phases. The top is different than the bottom. This is not the same, this is heterogeneous. So if you ever get milk from a cow, you get milk from a cow, what happens? It separates. Cream goes on top, milk on the bottom. That's a heterogeneous mixture. You can take milk though, and you can make it a uniform mixture, so called a homogeneous or homogeneous. Both of those are proper pronunciations. So I usually say homogeneous, except for milk, I say homogeneous milk. So it's either kind of thing. So if you get milk, it says pasteurized and homogenized. It's a homogenized mixture. It's the same mixture. The milk on the top is the same as the milk on the bottom. So these are mixtures. You can break mixtures down into pure substances. And pure substances can either be compounds or elements. So milk, you can break down into water. You can break it down to certain proteins. So you can break it down into minerals. So water is a compound. It is 2-part hydrogens to 1-part oxygen. So it's a compound is a combination of elements. There's calcium phosphate. That's another compound that's found in milk. So there's various proteins. There's casein. I can't pronounce it probably. Casein or something. That's a protein. That's made primarily of carbon, hydrogen, oxygen, nitrogen. Maybe a little bit of sulfur in there too. So those are all compounds, and they make elements. And you go with an element. Elements are the basic building blocks of, and we're just going to talk about atomic matter. There's other types of matter that we won't talk about in this class, but most of what we have to deal with in our day-to-day lives is really atomic matter. And the elements, there are 118 of them that we know of right now, and 92, well, it depends on your, this is also another opinion. So 92 plus or minus a few are found naturally on the Earth. The rest can be made synthetically. So, but we have 118, maybe 92 elements, depending on who you want to talk to. And all of these elements, so let's build up the other way. We have these elements. I'll go with the official answer. I guess the official answer is 118. 118 elements make compounds. Compounds are combination of elements. And then these combinations of elements and or compounds can make uniform mixtures, and combinations of elements, compounds, and mixtures can make non-uniform mixtures, heterogeneous mixtures. So build it up and break it down both ways. Question?
Can you go over the mixture part? Because it's hard for me to see the difference between homogeneous and heterogeneous. Like, it's not solid and liquid. Is it, or?
It just uniform versus non-uniform. Homo is uniform, hetero is non-uniform. So if the mixture is uniform throughout, it is homogeneous. If it's not uniform, it's heterogeneous. It doesn't matter the phase.
Okay.
So there are homogeneous. Homogeneous mixtures have to be the same phase.
Okay.
So air is a homogeneous solution.
Right.
So it's a vapor phase solution, and it contains, mostly oxygen and nitrogen. So two elements, and it's a uniform mixture. You can have liquid mixture. So vodka is ethyl alcohol and water. Two liquids. You can have metal. You can have solid mixtures. So like alloys. So 14 karat gold is a mixture of the elements gold, silver, and copper, and it's uniform. So, but you can also have non-uniform mixtures of the same phase. So if you've ever seen a meteorite before, like a metallic meteorite, it's typically nickel iron, and you have two phases of nickel iron. So it's just two elements, but they have different solubility against each other. So you get these like kind of stripes in them if you've seen them. So it's a mixture of two elements, but it forms a heterogeneous mixture. So, okay. Other questions? Did I answer your question?
Yeah.
So
I can focus on it more later.
Yeah. Milk. You're milking us now for information. All right. So, but with elements, the other way you can think of it is the elements are like letters. So the English language has 26 letters. And think of compounds as combinations of those letters to form words. So like the letter T and the letter H, or I'll do three letters, T, H, and E. So, T has a T sound, H is a H sound, and E has an sound, right? But when you form it together to form the word the T and the H have a different sound now. So the properties of T and H have changed in our language. And you see this with elements too. So many people are allergic to nickel, and most people are not allergic to titanium. But for dental, like for braces, it's an alloy of nickel and titanium is what they use for braces, and pretty much no one's allergic to it. So, but I mean, even people with nickel allergies are not allergic to nickel titanium alloys because the properties of those two have changed when you fix them together. So now we have words, and those words can then make stories. So you have letters that make words or compounds, and those compounds have stories. And how many stories can we write with 26 letters? Imagine if we had 118 letters to work. So that's a story of something like an iPad, right? We have many elements in these things. There's a lot fewer in the textbook. This is mostly carbon, hydrogen, oxygen, nitrogen. There's a lot of like metals and rare earths involved in electronics. So yeah. So any questions? And we're changing topics yet again.
Did you say letters are like elements?
Yes.
They're like compounds. Yeah, the third one.
Stories are like mixtures.
Thank you.
And that's just analogy. And that's my analogy, it's not the book's. Okay, new topic. So physical property. A physical property is something you can observe without a substance change. So things like color, magnetism, boiling points, So you're like, whoa, the boiling point. So you can take water. Water is solid water, ice. You can melt that to form liquid water. You can boil it to form water vapor. You can condense water vapor to liquid water. You can freeze liquid water to ice. So phase changes, you're still not changing the substance. Then there's chemical properties. Chemical properties deal with composition changes. So, or lack thereof. So actually, non-reactivity is also a chemical property. So physical properties you observe without a change in compound. Chemical properties you deal with a change more often, sometimes lack of. So my t-shirt that I'm wearing is flammable. That's a chemical property, right? Because if you light the t-shirt on fire, it's no longer a shirt, right? My t-shirt is blue. You're observing the color of it without changing the substance. So that's a physical property. So then with changes, and this is the Greek symbol delta. So, the letter, I should say letter delta. I guess the Greek alphabet, we use this quite a bit in science. So like here's alpha, this is upper alpha, lower alpha, this is capital beta, this is lower beta, this is gamma, and this is delta. So Greek is just like English. We have upper and lower case. Some of our letters are the same. Delta is, it's also RD, but delta, this is capital delta, and in science notation, it means change. So capital delta means change. So a physical change is a change of state, solid, liquid, gas state, and or appearance. So chemical change means a change in composition. Specifically, atoms are exchanged. So, or not exchanged. So in the case of gold, a chemical property of gold, silver, platinum, the noble metals, they're noble. Noble means they don't react. We'll learn about noble gases. They tend not to react.
If they don't run.
Yes. Well, silver can tarnish. Yeah, but yeah, more or less, yes, they tend not to. So here are some pictures. So, and the screen is terrible for you guys. So carbon dioxide here, for instance, this is dry ice in the middle of the picture. It sublimes, it changes from solid to gas, and that is a physical change. Sugar dissolves in water, so that's sucrose sugar. It's dissolving in water. It's not changing, it's still sucrose, although it changes state. You go from solid sugar to aqueous sugar. So you have a change in state, there's a physical change, but it's not a chemical change, but it's still sugar. Then you have propane, burning, and as you burn it, it changes from propane to carbon dioxide and water. So you've had exchange of atoms, that's a chemical change. So, and I know in a way I'm jumping ahead because I'm bringing up atomic matter and elements, and we haven't even covered that in class yet, but I think most people here have heard of atoms before. I've actually had one student that never heard of an atom before. So that was an interesting, like, ooh, this is gonna be interesting.
I met someone who had never used a stamp on an envelope last year.
Oh.
They did all of their banking and everything by electronic.
Oh, wow. Well, it's going to become more and more common. Okay, but energy. So changing topics yet again. So energy, and the definition of energy in the chemistry textbook is energy is the capacity to do work. So I don't have any kids, but I have nieces and nephews, and they have lots of energy. They could be doing work. They could be mowing the lawn. They could be washing the dishes. But are they doing that? No, they're just kids. That's fine. Right. So, but they have the capacity to do work. And the same thing with energy in chemistry class. And there's physics has a much better definition. And part of me just like, I want to talk more about energy, but this is a chemistry class, kind of thing. They have better definitions than we do. But a couple forms of energy. We have potential energy, and that's stored energy. Stored energy can be gravitational. So, right, if I have the old physics example, here's, I'm not going to do it, don't worry. You have stored potential energy, and You let it go, and this gravitational potential energy has now turned into kinetic energy. So kinetic energy is the energy of motion. And there's also radiation, electromagnetic radiation. Energy can be stored, or energy can be in the form of radiation. So we'll talk more about that when we get to further chapters. And I do like to mention this, though, the 4 fundamental forces, and I've listed 4 fundamental forces, or I've listed 5 of the 4 fundamental forces. So, what is a chemistry class that I don't contradict myself? You haven't found that out yet. I contradict myself a lot, but that's just because chemistry, yeah. But yeah, question?
That's the first time I've heard dark energy being a fundamental force.
It depends on opinion.
Okay.
So the fundamental forces, people have listed 3, some people list 5. So the fundamental forces are gravity. Gravity is only positive. It's the weakest force. And it is felt between all forms of matter and antimatter, and between matter and antimatter. So I mentioned matter. What's antimatter? Antimatter is the same as matter, except the charge is flipped and the handedness of spin. This is beyond this class, but the matter, we have a right-handed rule for so like magnet. So when you study physics, and if you have current going through the wire this way, so the magnetic field is right-handed rule. The magnetic field follows this direction around current flowing through. That's the right-handed rule. If we had a positron going through a wire, the magnetic field would go this way. So that's the difference between matter and antimatter, besides the charge. So in the handedness of the spin is the other thing. So and gravity exists for all matter and antimatter. Then there's electromagnetic force. So this is stronger than gravity. Basically, electromagnetic force, in a nutshell, is positives and negative attract, and like charges repel. And I'm not going to talk about magnetism. Although I did mention a little of the wire, but that's the level you have to kind of understand for this class. That's electromagnetic energy. And then we have nuclear weak and nuclear strong. So atoms are made of smaller particles called protons, neutrons, and electrons. Protons and neutrons are made of tiny particles called quarks. So the nuclear weak force is what binds the quarks to form protons and neutrons. It turns out the nuclear weak force is actually electromagnetic. So we have combined 2 and 3 together. That's one of the goals of physics right now, is have a grand unifying theory that combines all the aspects together. So we combined 2 and 3. We haven't combined the rest. Nuclear strong, in an atomic nucleus, you have protons. They're positively charged. They're repelling each other. You need to have a stronger force that keeps those positive charges tied in. We call that the strong force, or the nuclear strong force. So, and you can call it the nuclear weak, you can call it weak too. Strong force, weak force. You can add or subtract nuclear from that. And the last one I mentioned for dark energy, we don't know. So depends on whom you ask. For what the 4 fundamental forces are, you can list 3 or 5. So depends on the source. Yeah.
Is this theory relatively new, like 100 years? That's why it's.
Oh yeah.
Yeah.
Oh yeah. It's like less than 20 years.
Oh, okay.
I met the dude that Australian fellow. He won the Nobel Prize for that. He was a very, very charming individual. So
Nobel Prize
for discovering the expansion of the universe.
Okay.
That is expanding faster. Yeah.
Charming meaning what?
I mean, like, he was just amazing to talk to.
I see.
Very humble, and I was asking him all sorts of questions, and he was patiently talking to me and answering them. And because I'm a Y child. So, and there's my shut up alarm. All right, shut up alarm. Class is over. I know that I did talk, about a half an hour for COVID. I gave you a tentative schedule, and actually we can blow through this pretty quickly, but I am taking a lot of time. So some of the other stuff, I don't think we're going to take 2 class periods for chapter 3. So don't worry, we'll still be good. So, all right, so got my shut up alarm. Class is over, and I guess I got to stop the.
Is that all from chapter 1?
Yeah, we're still in chapter 1. Yeah, we're still gonna go in chapter one.